In paper 2, it's more usual to get a waves question that assesses lots of aspects of waves. So in this step 2 tutorial, we are going to have questions that we've already done in C2 or C3 and then move on to the standing waves element of it. So in question 1, A and B, the answers to those were already screencasted in C2 and you can find the answers to them there. They refer to different parts of the waves topic. But if we head to question 1 part C, you can see that we have a recognisable standing waveform here and we're going to answer the question on that now. C. One end of a string is attached to an oscillator and the other is fixed to a wall. When the frequency of the oscillator is 360 Hz, the standing wave shown is formed on the string. Point X, not shown, is a point on the string at distance 10 centimetres from the oscillator. Let's talk through the diagram before we actually go to the question. This standing wave formation has two fixed ends. And from step 1, mass of the majority, I asked that you memorise this equation for two fixed ends. We might use it, we might not, but let's put it down there anyway. We can see that the length of this system is 2.1 metres and there's a point X that's a distance of 10 centimetres from the oscillator. Well, given that the whole length of the system is 2.1 metres and it's split into 3 antinodes, then we can say that this point here and this point here, we know what they are. This is 0.7 metres, this is 1.4 metres, just simple maths. So we know that point X is around here. 1. State the number of all other points on the string that have the same amplitude and phase as X. If you remember in our mass of the majority tutorial, you'll remember that all points that are not separated by a node, i.e. here, or separated by an even number of nodes, there, are in phase. But this question says has the same amplitude as well. So at this point here, that particle will have the same amplitude and phase as point X. Then we go an even number of nodes across and we have a point there and a point there that has the same amplitude and phase as X. So we state the number, it's 3. And it says state the number of all other points, not state the number of all points. 2. The frequency of the oscillator is reduced to 120 Hz. On the diagram, draw the standing wave that will be formed on the string. The initial frequency is 360 Hz. The final frequency is 120 Hz. And you can see that that is 1/3 of the initial frequency. Bearing in mind that the speed of the wave will be the same because the material of the wave is the same, if this decreases by 1/3, then the wavelength has to increase by 3 to keep the speed the same. So we have to increase the wavelength of this wave by 1/3. We also have to bear in mind that we have to meet the closed conditions of the wave. So there has to be two fixed ends. And you can see that here's the patterns I'm drawing here with two fixed ends. They have to meet one of these patterns. Now, knowing that the wavelength is going to go up by 1/3, then the pattern is going to look like the first or fundamental harmonic. One big antinode with two nodes at either end. That's our answer to 2. Question 2. A pipe of length L has 2 open ends. Another pipe of length L' has 1 open end and 1 closed end. The frequency of the first harmonic of both pipes is the same. What is L' over L? Let's draw it. We've got 2 open ends and the wave pattern is going to look like that for the first harmonic. And in that case, L, we have lambda is equal to 2L. Let's go to the second lot where we have 1 closed end and 1 open end. The first harmonic is going to look like this. And the wavelength of that is lambda equals 4L'. If we want to rearrange for L, then L is equal to 2 lambda over 2. And L' is equal to lambda over 4. So L' over L is equal to lambda over 4, and then L is lambda over 2, which takes it up to there, which gives us a half because these lambdas cancel out. So the answer is D. Question 3 is a distance displacement graph of a longitudinal wave. We've actually answered the first two questions of this in C2, so we'll head down to B2 right now and start answering the rest of the questions. Show that the angular frequency of oscillations of a particle in the medium is omega equals. Well, we know the equation for omega is 2 pi f. We need to know what f is. We can see that the wavelength is 1.6 meters. And the previous question told us that the speed of the wave was 340 meters per second. So frequency is equal to 340 divided by 1.6. And we can pop that all into this equation here. And that gives us a value of 1.34 rads per second. In fact, I think we did answer that in C2, but there we go, we've done it again. C. One part in the medium has its equilibrium position at x equals 1.00 meters. 1. State and explain the direction of motion for this particle at t equals 0. So to 1 meter, x equals 1 meter, that's the point there. And then a moment later, it's going to have moved down. And it tells us explicitly that a displacement to the right of the equilibrium position is positive. So if it's negative, then it must be a displacement to the left. As the wave progresses, the graph will show a negative displacement for the particle. This means the particle will move left. Now, if you didn't understand that, I highly recommend you go back to C2. There was a couple of questions in exactly that vein in that tutorial. C2. Show that the speed of the particle at t equals 0.882 milliseconds is 4.9 meters per second. This is a higher level question from SHM. If you're a higher level student, this is what you should be using, and you'll find this from your data booklet. If you're a standard level student, please feel free to switch off. Haha. X0 is your amplitude. X is the displacement at that time, and omega is 2 pi f, and you've got all the data you need for up there. So pop in the details to that, and you should end up with an answer of around about 4.9 meters per second, as explained in the question. Okay, let's get to the actual standing wave stuff. The travelling wave in B is directed at the open end of a tube of length 1.2 meters. The other end of the tube is closed. 1. Describe how a standing wave is formed. You'll see this question a lot, so it's worth just memorising how it's done. What you would say is two waves of the same frequency, amplitude, and I would put speed in as well, travel towards each other after reflection, because they reflect and then they go back on each other. And then I would write the superposition of these two waves causes a standing wave to form. That's perhaps a little bit more wordy than you would need, but the concept is there. Two waves of the same frequency, amplitude and speed superimpose after reflection, causing the standing wave to form. 2. Demonstrate using a calculation that a standing wave will be established in this tube. Given that it's one closed end and one open end, I am immediately prompted to write down this equation here, and this is the equation I asked you to memorise in step 1, mass of the majority. I'm going to rearrange it for n, so n equals 4L over lambda. 4 times L, which is the length of the tube, is 1.2 meters, divided by lambda is 1.6, and that gives us a value of 3, which tells us that n is 3, that's a whole number. And given that n is a whole number, that tells us that one of these patterns is likely to form? I'm now committed to drawing all these patterns. You get the idea, okay? So if n is a whole number, it means that, there we go, this pattern forms, okay? If n wasn't a whole number, then a standing wave would not be formed in that tube. Question 4. Water is draining from a vertical tube that was initially full. A vibrating tuning fork is held near the top of the tube. For 2 positions of the water surface only, the sound is at its maximum loudness. The distance between the 2 positions of maximum loudness is x. What is the wavelength of the sound emitted by the tuning fork? What we have here is one open end and one closed end, and we're going to get a series of waveforms created in here. And you can see that the maximums are here, here, and here. And we can tell from the question that that's x. Let's look at that pattern and establish one wavelength. Well, one wavelength starts here, goes all the way up and then down again, and that's x as well. So the wavelength of one wave is actually 2x. Our answer is D. Question 5. The frequency of the first harmonic standing wave in a pipe that is both open at both ends is 200 Hz. What is the frequency of the first harmonic in a pipe of the same length that is open at one end and closed at the other? I'm going to draw this situation here. So this is situation 1. We have the first harmonic in a pipe that's open at both ends. And do you remember I did say to you, you must memorise this equation for that situation. That doesn't tell us anything about frequency, does it? Wait a minute. V equals F lambda, so lambda equals V over F. So instead of lambda here, let's put V over F equals 2L over N. And of course we're looking at the situation 1, so everything's labelled 1. Let's look at situation 2. Oh, I forgot to add something in. The length of that is L. The length of this is L2. And the first harmonic looks like this. Remember from first tutorial I told you to write this down when you see an open and a closed end. We're going to do the same. We don't have frequency, so we're going to do V2 over F2 equals 4L22 over N2. Right. We know that the length is the same for both of them, so we're going to rearrange both equations for L. L1 is equal to V1N1 over 2F1. L2 is equal to V2N2 over 4F2. L1 is equal to L2. So V1N1 over 2F1 equals V2N2 over 4F2. N's cancel because N is the same for both and it's the fundamental harmonic, so they are 1, so they go away. The speed of the wave is the same, so that can cancel out. So what we've got is 4F2 equals 2F1. So F2 is equal to a half F1. F1 was equal to 200, so half of that is equal to 100. The answer is question 5C. Question 6. The diagram shows a second harmonic standing wave on a string fixed at both ends. What is the phase difference in radians between the particle at X and the particle at Y? You can see that these particles are not separated by a node, and they both reach the maximum point and their minimum point at the same time. That means they're in phase. When they're in phase, then the phase difference is 0. If Y was here, it would be operating exactly the opposite phase to X, and it would be completely out of phase, and the phase difference would be pi. But in this case, that's not the question. The question is, what is the phase difference? And it's 0. Question 7. A pipe of fixed length is closed at one end. What is the third harmonic frequency of the pipe over the first harmonic frequency of the pipe? Let's draw these two diagrams. This is the first harmonic frequency of the pipe. And of course we write down this equation when we come across that situation. As in the previous question, we're not really that interested in wavelength. So instead of writing lambda, we're going to write V over F. So V over F1 is equal to 4L over N. And in this case, n is equal to 1. There's one node. So we've got v over f1 is equal to 4L. Let's rearrange for f1. f1 is equal to v over 4L. Let's look at the second situation, the third harmonic. That's a drawing of the third harmonic. There's 3 nodes. And again, we've got lambda equals 4L over n. But in this case, n is equal to 3. So we've got lambda, we're not going to write lambda, we're going to write v over f instead, equals 4L over 3. So let's rearrange for f3. f3 gives us 3v over 4L. And the question says, what is this ratio? f3 over f1. So instead of f3, we're going to write 3v over 4L. And f1 is going to be v over 4L, which means we take that up to here. That cancels, that cancels, that cancels, gives us a value of 3. The answer is C. Question 8a. A loudspeaker emits a sound towards the open end of a pipe, the other end is closed. A standing wave is formed in the pipe. The diagram represents the displacement of the molecules of air in the pipe at an instant of time. 1. Outline how a standing wave is formed. This is the same as last time. After reflection, 2 waves of the same frequency, amplitude, and speed meet and superimpose. The result is a standing wave. X and Y represent the equilibrium positions of 2 air molecules in the pipe. The arrow represents the velocity of the molecule at Y. 2. Draw an arrow on the diagram to represent the direction of motion of the molecule at X. We can see here that anything up that way is displaced to the right. At this point here, it's equilibrium. The diagram shows that its displacement is positive, which means its movement is to the right. 3. Label a position n that is a node of the standing wave. Well, the resulting standing wave is going to be like that. And here is our node there, n. 4. The speed of sound is 340 meters per second and the length of the pipe is 0.3 meters. Calculate in hertz the frequency of the sound. F equals v over lambda. We've got v as 340 meters per second, but we don't know lambda yet. Let's have a look at the diagram. The simplest way to do this is recognise that the length of tube is equal to 3/4 of the wavelength. Therefore, the wavelength is equal to 4/4 of the length. So that gives us 4 over 3 times 0.3. So we've got 4 over 3 times 0.3, which gives us a value of 850 hertz. Question 9. A student blows across the top of a cylinder that contains water. A first harmonic standing sound wave is produced in the air of the cylinder. More water is added to the cylinder. The student blows so that a first harmonic standing wave is produced with a different frequency. I'm just going to draw that just now. So that's what it's going to look like initially, and the same pattern is going to look after the water has been added. What is the nature of the displacement in the air at the water surface and the change in the frequency when the water is added? There's going to be a node at both points here. So the nature of displacement of the air at both stages is a node. So it's got to be C or D, not A or B. What's the frequency? Well, you can see here that the wavelength of this wave has decreased compared to that one. And if the wavelength has decreased, the speed stays the same, means the frequency must increase. So we want an increase in frequency. The answer is D. Question 10. Describe 2 ways in which a standing wave is different from a travelling wave. The first way is that a standing wave does not carry energy, whereas a travelling wave does. And the second point I would say is to do with phase difference. The phase difference of particles between nodes is 0. This is not the case for a travelling wave. A vertical tube open at both ends is completely immersed in a container of water. A loudspeaker above the container connected to a signal generator emits sound. As the tube is raised, the loudness of the sound heard reaches a maximum because a standing wave has formed in the tube. So the first harmonic is going to look like that. B1. Outline how a standing wave forms in the tube. After reflection, two waves, the same frequency, amplitude and speed, superimpose. This results in a standing wave. And maybe put pattern at the end. B2. The tube is raised until the loudness of the sound reaches a maximum for a second time. So if you remember the first time, we had the maximum with the first harmonic. The second time, we're going to have a maximum with the second harmonic, which looks like that. Draw on the following diagram, oh there we go, the position of the nodes in the tube when the second maximum is heard. We want to draw that. And then the nodes are positioned here and here. B3. Between the first and second positions of maximum loudness, the tube is raised through 0.37 metres. The speed of sound in air is 320 metres per second. Determine the frequency of the sound emitted by the loudspeaker. Well, frequency equals V over lambda. We know that V is equal to 320 metres per second, and lambda is actually 2 times the distance between these two maxima, because if you see here, these two maxima are heard here. That's half a wavelength. So a whole wavelength must be the distance, which is equal to 0.37. So the whole wavelength must be 2 times that, which is 0.74 metres, equals 320 over 0.74, which gives us an answer of 430 Hertz to 2 significant figures. Remember, all the data is given to 2 significant figures, so you want to give your answer to that as well. Question 11. On a guitar, the strings played vibrate between 2 fixed points. The frequency of vibration is modified by changing the string length using a finger. The different strings have different wave speeds. When a string is plucked, a standing wave forms between the bridge and the finger. Outline how a standing wave is produced on the string. The wave moves along the string and reflects at the closed end. After reflection, two waves of the same frequency, amplitude and speed superimpose. Word superimpose is really important. This causes a standing wave pattern. We've written this down a few times now, haven't we? Should be coming pretty standard for you. The string is displaced 0.4 centimetres at point P to sound the guitar. Okay, I'm going to draw a diagram here. So we've got 2 fixed ends and we have a standing wave formed. The length between these 2 fixed ends, as shown in the diagram, was 0.62 metres or 62 centimetres. And this is the equilibrium point. And what this question says is the string is displaced 0.4 centimetres, so it's got an amplitude of 0.4 centimetres. And then it's left to vibrate. Point P on the string vibrates, let's put point P here, with a simple harmonic motion in its first harmonic with a frequency of 195 Hertz. We've got 2 fixed ends here, so again from step 1 I said write down this equation when you have 2 fixed ends. And the sounding length of the string is 62 centimetres. Show that the speed of the wave on the string is about 240 metres per second. We've got this. We want to find out what this is, and we know what this is. Do you remember we took lambda and we said it's equal to V over F? So let's take that and plop it in up there. So V over f is equal to 2L over n. Let's pop in our numbers now. N is equal to 1 because it's the first harmonic. L is equal to 0.62 meters, that's the length of the string. V, we want to know, and F is given. Let's pop all those numbers into this equation. So we're going to rearrange it for V. I'm going to cross multiply to do that. So V is equal to 2LF over N, which is 2 times 0.62 times 195 over 1, which gives us 241 meters per second. And we want to put that to two significant figures because the data is given to two significant figures. B2. Sketch a graph to show how the acceleration of point P varies with its displacement from rest position. This is SHM. This is a key graph from SHM, and if you had any sense when you were looking at the SHM tutorial, you would have a common graphs section in your revision notes. And that common graph section would show you that acceleration is proportional to displacement. No, but not that way, is it? Because it's proportional to the negative value of displacement. So we're going to draw it like this. That shows that acceleration is proportional to negative displacement. B3. Calculate in meters per second the maximum velocity of vibration of point P when it's vibrating with a frequency of 195 Hz. We're going to use this equation here. V is equal to plus or minus omega x naught squared minus x squared. It's got a maximum velocity at the equilibrium. When it's at equilibrium, its displacement is equal to 0. So that brings our equation down to this. V max is equal to plus or minus omega square root of x naught squared, which simplifies even further down to, what is x naught? Well, x naught is the amplitude, which they told us earlier was 0.4 centimetres, which gives us 0.004 metres. Omega is equal to 2 pi f. We know that f is 195, so it's 2 pi times 195. Let's pop all this in. Plus or minus 2 pi times 195 times 0.004, and that gives us a value of 4.90 meters per second. C. The string is made to vibrate in its third harmonic. State the distance between consecutive nodes. Third harmonic will look like, wait a minute, let's just draw diagrams. That's the first harmonic. Second harmonic looks like this. Third harmonic looks like that. And we want to know the distance between these nodes. 0.62 is equal to 3/2 of a wave, because that's 1.5 waves. Oh, it's really simple. All we have to do to find the distance between these two nodes is take a third of 0.62. Question 12. Let's just do all the questions today, shall we? A longitudinal wave travels in a medium with a speed of 340 meters per second. The graph shows the variation with time of the displacement x of a particle P in the medium. Positive displacements on the graph correspond to displacements to the right for particle P. It's a longitudinal wave and it's a displacement time graph. What can we find from a displacement time graph? We can find the amplitude and we can find the time period. Calculate the wavelength of the wave. Well, the time period is equal to 4 milliseconds, which tells me that the frequency is equal to 1 over 4 milliseconds, and the speed is equal to 340 meters per second. So we use the wave equation. Lambda equals v over f, 340 divided by 1 over 4 times 10 to the 3, so it's times that. 1.36 meters. What's all the data given to? Right, our data is given to two significant figures at most, so we're going to say 1.4 meters. Another wave travels in the medium. The graph shows the variation with time t of the displacement of each wave at position p. The dotted line represents the wave later on, a time later. State the phase difference between the two waves. T equals 0, the wave starts here, and the next time it reaches a peak at the time later is here. You can see that that is 1/4 of a wavelength difference, and 1/4 of a wavelength relates to pi over 2, a phase difference of pi over 2, or it can be 3 pi over 2. B2. Identify a time in which the displacement of P is 0. This wave is moving, and at this point here, let's just choose, I'm going to choose somewhere that's pretty obvious to me. Around about here, this wave has a negative displacement, and then a time later, it's got a positive displacement. So moving between those 2 points, it's likely to have a net displacement of 0, because if you add those 2 displacements together, it adds up to 0. So I'm suggesting that identify a time at which displacement of P is 0. That's going to be halfway between these 2 waves, which tells me it's 1.5 milliseconds. B3, estimate the amplitude of the resultant wave. Now, if these waves were in phase, then the amplitude would be 2 times 6 micrometers, but the waves aren't in phase. So where's the point? Let me just delete all this. So at what point are these waves going to superimpose to give the highest amplitude? Well, they're going to superimpose where they've both got the highest positive value, and it's at this point here. So you can see at this point here, both waves have a displacement of 4 micrometers. And if we add those two at that point, that will take us up to 8 micrometers. So it's 8 micrometers. Finally, we get to the standing wave stuff. A standing sound wave is established in a tube that's closed at one end and open at the other. The period of the wave is t. The diagram represents the standing wave at t equals 0 and t equals t over 8. The wavelength of the wave is 1.2 meters. Positive displacements means displacement to the right. And you can see that this whole wave here is 3/4 of a wavelength, which tells me that the length of this tube is 0.9 meters, because that is equal to 3/4 of the wavelength, which is 0.9 meters. Oh, which is actually C1. Okay, calculate the length of the tube. The length of the tube is L equals 3/4 times the wavelength, which is 0.9 meters. C2. A particle in the tube has its equilibrium position at the open end of the tube. State and explain the direction of the velocity of this particle at time t over 8. So it starts here, and at time t over 8, you can see at this point of the wave, t over 8 is going to be above it. So t over 8 later is going to be there. So it's moving towards that, which means it's got a positive displacement, which means it moves to the right. Now we're moving on to resonance questions. Question 13. A pendulum bob is displaced until its centre is 30 millimeters above its rest position and then released. The motion of the pendulum is lightly damped. Describe what is meant by damped motion. Do you remember in step 1 we talked about 2 conditions? The first condition was that a resistive force opposes the motion. And 2, that the amplitude or the energy decreases with time. The envelope of the oscillations decreasing with time. Question 14. A driven system is lightly damped. The graph shows the variation with driving frequency of the amplitude of oscillation, and we're very comfortable with this graph. On the graph, sketch a curve to show the variation with the driving frequency of the amplitude when the damping of the system increases. Do you remember from step 1 when we talked about the damping getting more heavy, then actually the frequency of resonance decreases a little bit. So what we want to do is we want to make it not get as big an amplitude, but we also want to decrease the point where that resonant frequency is. So there we are there. Let's move it along a bit. Let's have our resonant frequency about there and damped. So we're going to draw our diagram like this, hitting a resonant frequency around about there, and then damping down and hitting up like that. 2 marks there. The first mark will be showing that the resonant frequency has decreased. The second mark showing that the amplitude has decreased, but also that the shape of the curve is the same. Question 15. A farmer is driving a vehicle across an uneven field in which there are undulations every 3 metres. The farmer's seat is mounted on a spring. The system, consisting of the mass of the farmer and the spring, has a natural frequency of 1.9 Hz. Explain why it would be uncomfortable for the farmer to drive the vehicle at a speed of 5.6 metres per second. Well, given that we've been told the natural frequency of something, I'm reckoning that we have to do with resonance. And resonance occurs, which would be uncomfortable for the farmer, when the driving frequency is equal to the natural frequency. So we have to show that the driving frequency of these undulations is equal to the natural frequency of 1.9 Hz. The time between undulations can be found using the speed equals distance over time equation. So time is equal to distance over speed, so it's 3 metres divided by 5.6 metres per second, and that gives us a value of 0.535 seconds. So every 0.535 seconds, the driver will feel a bump. We can find the frequency of that by doing 1 over. There's 1 over 0.535, which gives us 1.86 Hertz, which is 1.9 Hertz. The driving frequency as a result of the undulations at 5.6 metres per second matches the natural frequency of the spring resonance occurs. It's a good question, that one. I like that. Question 16. The natural frequency of a driven oscillating system is 6 kHz. The frequency of the driver for the system is varied from 0 to 20 kHz. Draw a graph to show the variation of amplitude of oscillation of the system with the frequency. So it's 6 kHz, we know it's a maximum. Let's get the ruler out. We want to have our maximum amplitude at 6 kHz. And we want the shape of the graph to look like that we've got in our notes. We don't ever really want it to go down to 0. Question 17. A railway track passes over a bridge that has a span of 20 metres. The bridge is subject to a periodic force as the train crosses. This is caused by the weight of the train acting through the wheels as they pass the centre of the bridge. The wheels of the train are separated by 25 metres. I think this is already like the farmer's question. A. Show that when the speed of the train is 10 metres per second, the frequency of the periodic force is 0.4 Hz. This is the same as the farmer's question. The time between periodic bumps is equal to distance over speed, and the distance is 25 divided by 10, which gives us 2.5 seconds. Frequency is equal to 1 over time period, so 1 over 2.5 gives us a value of 0.4 Hz. The graph shows the variation of the amplitude of vibration A of the bridge with driving frequency FD when the damping of the bridge system is small. B. Outline with reference to the curve why it's unsafe to drive a train across the bridge at 30 metres per second for this amount of damping. So we go to the resonance point and draw it down, and that tells us that the natural frequency is 1.2 Hz. Let's work backwards. Time period is equal to 1 over frequency, so it's 1 over 1.2. The time period is 0.83 seconds. That means the speed is equal to distance over time, so it's 25 over 0.83, which gives us an answer of 30.1 meters per second. So outline with reference to the curve why it's unsafe to drive a train across the bridge at 30 meters per second for this amount of damping. At 30 meters per second, the driving frequency is 1.2 hertz, which matches the natural frequency of the system. Resonance occurs. My hands are beginning to get tired now. Oh, perfectly timed, because that is at the end of all these lovely questions. I hope you've enjoyed this tutorial.